seminar here, offered through the Rutgers Energy Institute, and I see a lot of familiar faces. My name is Rachel Schwam. I'm the Associate Director of the Energy Institute. Frank Felder is the Director here. But
I think he said he had to teach this time.
To teach this. Oh, because we pushed it forward, probably, yeah. And I'll just, we're very happy to have Joe Brodie to give a talk. We had him for the spring and we had to reschedule, so we're very happy with our, the current state emphasis and interest on wind energy. We're very excited to kind of be able to make a lot of use of our Rutgers expertise here. And but first, I just want to mention we also kind of flagged for you our next talk is Friday, October 12th at 10:45. I believe it's back in this room, and it's L.P. Weber, who's over at Princeton now, used to be at Columbia, very well-known psychologist who kind of studies energy and climate change decision making. So she'll be giving a talk on October 12th. So that's our next one. But I'd like to introduce Joe Brodie. He is kind of Rutgers
born and bred, I guess.
Born and bred. I saw you grew up in Monmouth County.
I did.
Where'd you grow up?
I grew up in Marlborough Township.
Oh, okay, Marlborough. So he got his BS in meteorology from Rutgers University in 2005, and after working for a while, he came back here and got a PhD in marine studies with a concentration.
That was at UD, sorry.
I'm sorry.
That's okay. Oh, did it not say where?
Oh, it says it eventually.
Oh, okay. Sorry.
That's why I was like, Rutgers all the time?
No.
I read it and forgot. Sorry, at University of Delaware. Makes sense. Marine studies with a concentration in physical ocean sciences and engineering, and has joined the RU Cool program as the director of atmospheric research. So we're very happy to have him.
Thanks.
Here today.
Thanks. Hold on, I forgot I didn't turn this on. Let's see if this works. All right, can everyone hear me okay? I have a loud voice, so I might not need it, but I do what I'm told, so. So thank you, Rachel. I'm very excited to be able to present today. So as Rachel said, I've been here at Rutgers, back here at Rutgers, I guess, since last summer. So it's been just over a year since I got back. And so I'm going to talk a little bit today. That's probably the longest title I've ever written for a seminar. So I've got a couple topics I'm going to talk about, some of which is from my PhD work, some of which was recently published, and then some new work that we're doing here at Rutgers. Okay. So first, I have a few acknowledgments. As I said, some of this content is from my dissertation, so I need to recognize my dissertation committee. So at UD, I had Dana Verone was my advisor, who some of you may know already because she used to be a faculty member here at Rutgers. And Fabrice Verone, Christina Archer, and Julie Lundquist, who's at the University of Colorado Boulder. And then for some of the work, the ramp prediction work that I'm going to talk about today, I have a couple grad student collaborators who were grad students at the time, Yossi Shirazi and Justin Gilchrist. I'll talk more about that work later on. And then, of course, now here at Rutgers, I, of course, work for RU Cool. So the whole RU Cool team, but in particular, I work a lot with Travis Miles. And then Saj Lichtenwalder, who's in the back, who helps with a lot of the stuff that I do. And then my student, Brian, is it Frey or Fry? I always mix that. It is Fry, right? Yeah, okay. And of course, I need to acknowledge my funding here at Rutgers and funding for a lot of the work that we do here at Rutgers in this area is provided by New Jersey Board of Public Utilities. So a brief outline of what I'm going to go through today. I'm going to do some introductory slides. I'm sure a lot of you are already familiar with offshore wind, but in case you're not, I'll do a little bit of background material. I'll dive into some discussion on making wind farm layouts and how you can relate that to climatology. And then I'll talk about a topic that's near and dear to my heart, which is the prediction of ramp events, which are sudden changes in wind speed that impact the production of wind farms. And then I'll talk about mesoscale modeling as a whole, using it for resource assessment in a couple different ways. And I'll talk about what we're working on next. So offshore wind power, there's a tremendous wind resource off of the mid-Atlantic coast for offshore wind. There's a couple figures here that help highlight that. This is from a paper by Mike Dvorak back in 2012. You can see that we've got capacity. So a capacity factor is the ratio between how much power you would get out of a wind turbine if it was producing full power all the time, and how much you'd actually get based on what the winds typically are doing. And so over land, a capacity factor of 30% is pretty good. You can see off the mid-Atlantic here, we're looking at 40, 45, 50, or even higher percent capacity factors. And so it's a tremendous resource that is also co-located with a very populated part of the country, the Acela corridor, if you will. New York, Philadelphia, Baltimore, Boston. And so the power doesn't need to go very far in order to get used. One of the challenges with building wind in the Midwest is there's no one there to use the power. And so they end up having to transport it via very long, power lines to get it to the source, to the places where they actually are using the power. That being said, I think everybody here knows that offshore wind is still very much a young industry, at least here in the United States. So far, the US has one operating wind farm, which is the Block Island Wind Farm, in that photo there, when I got to take a trip up there. And that's only 5 wind turbines. So we're still very much in the youthful part of this industry. Contrast that with Europe, where one of the wind energy developers, Ørsted, who built the first ever offshore wind farm, actually just retired their first offshore wind farm this year because it was operating for 25 years. So there's a lot of history on how to do it. It's just it's new for us here in the US. And again, something that's probably no surprise to any of the atmospheric ocean people in the room, the dynamics of the offshore environment are very different from when you build wind turbines over land. So again, for a quick review of what's going on right now to kind of set the stage, this is a map from BOEM, the Bureau of Ocean Energy Management, part of the US Department of the Interior. And they're responsible for all of the offshore wind leases, all energy leases that are on the continental shelf beyond state boundaries. So that includes oil, natural gas, but also wind. And so as of now, there are 12 leases that are already existing. I tried to, yeah, good. I got these little stars to try to show you where they all are. So that first one is Coastal Virginia Offshore Wind, which is another small, I believe it's 3 wind turbines. That's like a demonstration project like Block Island. And that's a joint venture between Dominion Energy and the developer Ørsted. Vineyard Wind off of Massachusetts. I should also add those dates are dates that BOEM anticipates as being dates when those farms become operational. So that helps set the timeline for what's coming in the next 10 years. So South Fork, which is one of the Deepwater wind farms. Deepwater is the developer that runs Block Island. Ocean Wind, which is the Ørsted farm that's off of New Jersey here. They have the southern half of the New Jersey lease area. Bay State Wind, which is Ørsted's project off of Massachusetts. US Wind, they have a project off of Maryland. Revolution Wind, which is another deepwater project off of Massachusetts. Why is it not changing? All right, I guess we'll use this. Oh, did I jump a little? Sorry. So next up is what they're calling the Skipjack Wind Farm or Garden State Offshore Energy. They're kind of splitting the region. That's the region off of Delaware. Basically, the lower half, they're planning to sell that power into Maryland as Skipjack, and the northern half, they'd like to sell that power into New Jersey as Garden State Offshore Energy. I won't tell you how the folks in Delaware feel about that. Then there's Dominion Energy has a commercial scale farm that would be adjacent to their test farm that they're building now. US Wind also has a wind farm. They own the northern lease off of New Jersey. Empire Wind is the project off of New York Harbor. That's the company now known as Equinor. They were formerly Statoil. And then there's a farm proposed off of Kitty Hawk, North Carolina by a company called Avangrid that does a lot of land-based wind. So there's a lot of activity in the next 10 years. The industry may be getting off to a slow start, but all signs indicate that the industry is about to ramp up. And this is led.
These are all going to be built?
All of these are in some level of project development. So all the properties have been leased out. Many of them, especially in the early half, have submitted construction plans to the federal government. So they are moving forward. All the permits are putting in place. Some of them, like I know US Wind has been deploying. They built Met Tower in their area to start doing resource assessments. Ørsted deployed 2 floating LiDAR buoys in their area off of New Jersey just this summer. They also deployed 2 in their area up off of Massachusetts. So they are supposed to legitimately legit projects. And the big question for a lot of us is, the federal government right now doesn't seem like the type of, they're that enthusiastic about something like offshore wind, right? And so a lot of this is actually being driven by state investment and state renewable energy goals. And so as an example, so I put up here, this is also from BOEM, actually from a meeting I went to last month, so it's up to date as of then. States have commitments to purchase a certain amount of power from offshore wind. A lot of this is legally mandated because it was legislatively passed. And so you can see what's nice here, New Jersey, led by Governor Murphy, is at the lead of the pack here, committing New Jersey to purchasing 3,500 megawatts worth of offshore wind capacity, with a renewable goal of 50% renewable energy for the state of New Jersey by 2030. And so in total, we're talking about roughly 8.5 gigawatts worth of offshore wind that the states have committed to building, purchasing, and actually using the power from. And so to break down New Jersey into a little bit of detail, they've broke it down into 3 solicitations. This announcement came just last week. The first solicitation is actually, they opened the period just yesterday. So the developers are allowed to submit proposals for an offshore renewable energy certificate in order to provide power to New Jersey. So that process is going on right now for the first 1,100 megawatts. And then the next 1,200 megawatts in 2020, and then the 1,200 after that in 2022.
I got a question.
Yeah.
So how come the lease area of the New England looks so much bigger than the other areas, but when you add up those megawatts of Massachusetts, Rhode Island, even if you're at Connecticut, it's much smaller than the amount of power?
That's an excellent question. And the reason for that is, even though those leases all exist, the state has only so far committed to purchasing that much power. So eventually they're going to commit to larger numbers. This is just their initial step, and New Jersey has kind of tried to push forward a little bit more than the others. The lease areas off of here can support considerably more than that. And they actually, so Massachusetts did their first solicitation a couple months ago, and of those 4 developers off of Massachusetts, those 4 projects, only 2 of them were initially awarded renewable energy certificates to initially provide power. So the other projects are still ongoing, but the state hasn't committed to purchasing the power yet. So it's still very much, this changes every couple of months. Yeah?
I think it'd be important to clarify that. I don't think that the state is actually purchasing.
Right.
I think we want to not.
Yeah, I think you're right. It's not that they're permitting the selling of the power into the state, I think might be a better way to word it. Yeah, yeah. That's one of those things I always have trouble, as a scientist, I guess sometimes I mix up the language on that a little bit. In any event, so for comparison, in the news this week, you may have read that Oyster Creek Nuclear Power Plant just shut down this week. And so that particular nuclear power plant was a 626, I believe, megawatt reactor, 636 megawatts, excuse me. So for comparison, this capacity is a little less than double, like 2 Oyster Creeks. Now that being said, wind doesn't provide power 100% power all the time. So at a capacity factor of say 45%, we're probably talking about this amount of power capacity roughly replacing a plant the size of Oyster Creek. So what are some of the challenges? And there's lots of them. And I'm going to focus on a couple of the atmospheric ones, because that's my specialty. There are many, many others that are being explored by others in this room. The first one I'll talk about is a wind turbine wake. And this is a wonderful image that every single presentation I've ever seen about wake effects has this picture in it. And it was captured by Vattenfall in one of their European wind farms. And the atmospheric conditions were just right that day for these contrails to form in the wake of the wind turbines. And so you can literally see the wakes propagating from one wind turbine to the next. And the way I always explain this is a wind turbine wake is like a shadow. It's a wind shadow. So the turbines at front, they're collecting energy, they're extracting energy from the wind, and in doing so, they are reducing the wind speed. And so it produces a turbulent wake that has lower wind speeds behind it. And then this gets propagated through the farm, the effect gets magnified to the point where under certain circumstances, you can experience a 40% reduction in power production. This is from a study of a European wind farm by Rebecca Barthelme. You can experience a 40% loss sometimes of production from wind turbines solely because of this effect. And so it's something that folks are spending a lot of time on to try to improve. And one of the ideas to do that is to scatter the way the wind turbines are arranged so they're not in lines. That presents its own challenges because fishing can't happen in areas where the turbines are scattered all over the place. They kind of need them to be in straight lines or they can't fish between them. So there's a lot of competing interests that need to be balanced in order to make offshore wind successful. So this is one example of a challenge in the atmosphere. Another, specifically for this region, is the variation between the seasonal variation in electrical demand and the wind that we see. So probably most of us just anecdotally are familiar that wind is stronger in the winter and weaker during the summer. However, when do we use the most power? During the summer. We use air conditioning, everything else. And so the peak in wind speed and the peak in power consumption are not lined up. And so the question is, when you're designing things like wind farms, are you looking to get the most amount of power that you possibly can, regardless of the season, or are you going to try to capitalize when to get the power? You want it when you need it the most, right? And so the wind regimes are different in the summer versus the winter. They come from different directions at different intensities. And so when you're designing a wind farm to better capture energy, you need to think, okay, should I be maximizing in the summer? Should I be maximizing in the winter? And that's a question for developers and for utilities, when do they want and need the power? And then most importantly, I guess, focusing on the work that I do, how do various phenomena in weather impact the production that you might see from a wind farm? To dive into the electrical load question a little bit more, this is, I guess, a heat map, I suppose is a good way to put it. Oops, sorry, I hit the wrong button. All right, my pointer does not like me today. So on the x-axis here, I have hour of the day, and on the y-axis is month of the year, starting with December here, going up to November. So, so winter, spring, summer, fall. And you can see there's a huge amount of electrical demand. This is for the entire PJM network. PJM is the electrical, the grid operator that operates the electrical grid for New Jersey and a multitude of other states. You can see very clearly this summertime peak late in the day during the summer months because of air conditioning. You also see these smaller peaks during the winter that coincide with this morning time here when people are getting up, getting ready for work, going to work, turning on their lights at the offices, factories are spinning up, everything else that happens at the beginning of the workday. And then this other peak later in the day when everybody gets home from work, starts cooking, puts on their televisions, does all the things that they do in the evenings. And so you see a different pattern here in the winter that you don't see during the summer. And I'll spend some time on this a little bit later. As an atmospheric scientist, I have to include one equation. So for those of you who aren't physicists or engineers, I promise you this is the only one. WRF is the model that I'm using for the studies that I'm talking about today, which is the weather research and forecasting model, which is a very widely used atmospheric mesoscale model. It's used both operationally and it's also used for a variety of research endeavors. And as of version 3.3, which at this point now was like 9 years ago when I started graduate school, again, I hit the wrong button. They built in a wind farm parameterization tool. And so what this does is it basically inserts this little rotor disk of area A into the atmosphere, and it serves as a kinetic energy sink, basically a source of drag that converts some of that kinetic energy into electrical energy and then dissipates remaining energy as drag in the form of turbulent kinetic energy. And then this extracted kinetic energy, as I said, results in a change in the wind speed, in addition to, of course, a power, right? And so basically what the model does is it just adjusts the wind velocity you can see this is basically 1/2 mv squared. So it's the equations that we're all familiar with. And it just does that on a grid size scale. So if you have more than one wind turbine in a grid cell, it would add them up. So that's why you have all the indices. So now we'll dive into the first topic on wind farm layouts. And so for this study, and actually for most of the studies that I'm going to talk about, I was using the Delaware wind energy area off of Delaware. Since a lot of this was done while I was at Delaware, it kind of made sense at the time. Yeah, I don't know why. So what I did for this part of the study. So WRF has two modes. You can run it in an idealized way where you're idealizing the environment. It's basically just a simple grid box that you make a domain, and it's not realistic in that it's not an actual segment of the Earth. But the advantage to that is you can do whatever you want. And so I created some idealized wind farms in the model. Each of them contained 36 wind turbines. Each of them is a 5 megawatt capacity, which nowadays is small, but that was state of the art back when I was starting graduate school. Now we're up to 8 and 10 megawatt machines, and I believe they're even working on a 15 megawatt machine. So it's tremendous how they've grown since then. They all have 100-meter hub height, so the hub of the wind turbine at 100 meters. They're all 1 kilometer apart, and I have the grid set up so that the grid is every half kilometer, so I can see a little bit of what's happening in between the wind turbines, which is very much pushing the limits of the mesoscale model. And then I set it up with a 13 meter per second wind speed, so a constant wind speed in a neutrally stable atmosphere. And I keep forgetting that the clicker doesn't want to work. And so we have winds coming out of what would be the west, is signified by the blue arrow, and the colors here are actually reversed to try to highlight where the winds are weakest. So red is bad, basically. Red is where you're going to get the least amount of power because the wind speeds are the weakest. And so you can see as you have wind farms that have more wind turbines in a row, I guess it's probably intuitive that you end up with weaker winds at the back as more and more wind turbines are extracting their energy. However, some of these shapes allow more turbines to be at the front, so to speak. So as opposed to say this square or this rectangle where you only have 4 wind turbines at the front, you actually have quite a few if you have, say, an arrow pointing into the winds. And so this figure here shows calculated power output based on the wind speed. And again, sorry. And then this compares to some of the modeling work from that Barthelemy study that I mentioned earlier. Obviously it's not, so again, the mesoscale model isn't as refined as some of the models that they used in this study, which a lot of them were large eddy simulation models, or models specifically designed to do wind energy resource assessments. So we're not seeing the huge drop off initially, but we definitely do see a decrease down to about 70% by the back of the farm. So the tool is useful, it's not perfect, but it gets us somewhere. And it's the utility of the tool itself, the fact that it's WRF, that you can actually use real atmospheric parameters a lot more easily than you can in some of these other models, and the fact that it's fairly computationally efficient. So in order to calculate, I talk about this, actually, I'll talk about this in the next slide. So in order to actually assess how a wind farm would perform under a typical wind environment, obviously winds coming out of the same direction all the time on very simple geometric shapes doesn't get us the answer, right? And we all know winds are highly variable. And that's one of the challenges with building wind farms, especially in our region, where we have 3 predominant wind directions, out of the northwest, the northeast, and out of the southwest. And so how do you lay out your wind farm? If the winds blew from different directions equally at all times, a circle would be great, right? Because then you'd always be capturing. And if the winds always blew from the same direction, you'd probably want to build one straight line that is perpendicular to that wind direction. But of course, the real world doesn't work that way. And so for this part of the study, I took a conventional rectangle, so to speak, which has 90 wind turbines in it this time, for a total capacity of 450 megawatts, which at the time was what they were proposing for what was then the Blue Water Wind Project off of Delaware. And then I also put in this custom shape, which basically highlights, we have these triangle corners in the 3 predominant wind directions to try to capitalize on the number of wind turbines that are capturing the front winds. And so using the model, I basically, very simply, since it was an idealized model, I initialized the model with all the various wind speed bins from that windrow. So the speed and direction, so it was about, I think, 300 plus different wind speed and direction combinations. And then I ran the model to calculate what the winds look like. And as I said, this is fairly computationally efficient. I was able to calculate, using a wind climatology basically, how much power you would get out of the farm in roughly a few hours, as opposed to running an LES model, which could take weeks or even months. And so this is highlighting those three most predominant wind directions, and I blew up the one in the middle to kind of make it easier to see. And so you can see here in the standard rectangle, there's a huge wind deficit here in this back corner, where you're just not generating as much power, which goes away in the custom shape, because you have less wind turbines in the way, and there's also, I call this a courtyard. Dana always like to call it a keyhole, where you don't have wind turbines, and so it gives the winds a chance to recover some of the wake losses. And so ultimately this meant that in all three of the predominant wind directions, the custom shape produced more power. You can see that here in instantaneous power production. And so when you sum this up, you use that wind rows distribution to calculate the total power output over the year. And so ultimately, that resulted in roughly a 1.5% to 2% improvement in wake losses, which doesn't sound like that much, right? It's not too much, right? That adds up to, at the rates they were considering for blue water wind, almost $4 million. And so developers get really excited about very small improvements in efficiency, because any improvement helps make the project more financially viable. And so to highlight this, these distributions up here are trying to highlight what's going on. So this is winds coming out of the 200-degree direction. And the axes are the same here. So power output on the bottom, the number of wind turbines in the farm that were producing at that level. And you can see that in the rectangle, we actually have no turbines producing at maximum, whereas we have 3 in the custom shape. And we also have fewer turbines, even though we have a wind turbine here that's producing less power than any of the ones in the rectangle. There's only one of them. And if you combine these 2 bins, you have 8 versus 13 total turbines. So you're basically skewing the distribution a little bit on the high end. So that was looking very idealized, right? Very small scale. And also looking at averages. Like I was looking at climatology. I wasn't looking at, day-to-day variability. I wasn't looking at how wind speeds change. We all know how turbulent and variable wind is, right? So now we're going to dive into another problem, which is the short-term forecasting problem. And for those of you who are meteorologists, you know how tricky it can be to forecast the wind. And when a meteorologist, say at the National Weather Service, does a wind forecast, he might typically say, winds are going to be winds are going to be 10 to 15 miles an hour, which to you and me is probably fine. If you're going out, that's a pretty good speed range, right? To a wind energy developer, that's garbage, because power is a cubic function of speed. The amount of power that's available in the wind is a function of the cube of the wind speed. And so as an example, this is what we call a wind ramp event. So a ramp event is a sudden change in wind speed that's driven by some sort of meteorological phenomena. And so you can see here that the wind speeds are changing from roughly 4 meters per second here up to about 14 to 15 meters per second in a relatively short time. This is about 2 hours. But what does this mean in terms of power? You can see for an 8 megawatt wind turbine, that means you're going from producing no power at all to full power in a less than a 2-hour time window. And that's a tremendous change. And it's very challenging to predict, because if you're off by an hour or 2, you may have miscalculated how much power you could provide to the energy grid. And the forecast is tricky in a number of ways. You could get the timing wrong. So, this curve may occur an hour too earlier or later in the model than you see in observations. Or you could get an intensity error where the ramp might be stronger or less strong than you predicted. Or a shape error where it might happen more rapidly. So we have cases in our case study where it went from 0 to 8,000 in one 10-minute interval. That's huge and almost impossible to predict with any level of accuracy. And so this is, while numerical weather prediction has improved tremendously over the past decades, it's not good enough for the wind industry, because saying, winds are going to be from 6 to 10 meters per second makes a big difference in the amount of power that you're going to get. And so that's one of the challenges that we face as weather forecasters. How do you get this better? So what we did is we built a wind detection algorithm. I did want to prelude this, I forgot to mention this. So this project, I'm excited. One of the reasons I like this project, so when I was at University of Delaware, we had a graduate class that was offshore wind energy, science, engineering, and policy. And it was an interdisciplinary course. It was taught by 3 faculty. Dana Verone taught the science stuff, the atmosphere, the ocean. Then we had Willett Kempton, who taught engineering and some of the economic aspects. And then Jeremy Firestone, who's a legal expert, talked a lot about the law and the policy around offshore wind. So it was a truly interdisciplinary course. And the way the course was designed, the graduate students, we formed small groups and we had to do a group project. And the projects were comprehensive enough that typically one of the groups each semester had a project that would be like, okay, this is pretty good. Let's take this to the next level and actually do a paper on it. And that semester, the project that I worked on with Yossi and Justin turned into one of those, let's take this further. And so this project was one of those things we had no funding for. We really had no time for after that class, but we managed to keep it moving over the years throughout all of our other work, and managed to produce some really good results. And it was a good example of how when you get some interdisciplinary students together in a class like that, you can have some ideas that can really help the industry. So in any event, so how did we pick out ramp events? So Justin built an algorithm in MATLAB that could pick out ramp events from the wind record. And so what we looked for was a 50% increase in the expected power output in a time interval of 1 hour or less. We were using 10-minute winds in this case, we were using buoy 44009 off of Delaware. And using that algorithm, we detected 428 ramp-up events between March of 2005 and December of 2012. And in order to model these, we're not going to model all of them, right? There's only so much time we could do this. We selected 12 monthly analogs to represent the average event. And the way we did this, I have this figure here to depict the January historical analog. What the algorithm did is every ramp event that occurred in Januaries during that time interval, it averaged them all together, which gives you this blue line. And then what the algorithm did is it went through and found the ramp event that most closely matched that blue line. And then we considered that to be the average event for that month, and we modeled that one. So we had an actual meteorological record that we could model with in the real WRF model that's actually using meteorological data, not an idealized setup. And then we also selected 12 so-called extreme events that were extreme because they may have been a tremendous change in power, or a very short one where it may have ramped up very quickly and then ramped down again. Or it happened at a time of day or time of year where we felt that it would have bigger impacts on grid operations. And so what did we learn? Well, I guess probably no surprise to anybody here. Sometimes the model does well and sometimes it doesn't. And so as an example here, this event here from December of 2006, overall, so the black line is observations from the buoy. And then the red, blue, and green lines are 3 different versions of WRF we were running. We were using different we were using different forcing data for each. So the red line used the North American model, the NAM model, to force it. And then the blue and green lines were 2 different resolutions of the GFS model. And so in this case, the models did okay. They predicted a ramp. Obviously, you can see it's a lot more gradual than what actually happened, but it wasn't terrible. In this case here, in August of 2007, the model force with NAM basically didn't even see it. It had the wind speeds high the entire time. And the model force with GFS, it predicted a ramp, but not until, about an hour and a half, 2 hours later. And so that adds up to problems for grid operators. And so what we looked at, this middle chart here is showing the error, so the difference between observations and modeled. And I'm going to point out that most of the time you do modeled minus observed. to calculate how off the model is. In this case, we're doing observed minus modeled. And the reason for that is that then when you have a positive error, it means your observations indicated a higher wind speed and therefore a higher power production. And so a positive error means you have surplus power. And a negative error means you suddenly don't have as much power as you thought you would, and you need to find that power somewhere else, which typically means ramping up natural gas. And then this bottom curve here is the first derivative of that error. So how is that error changing over time? And so what you see here is, for instance, this sudden change here is where you go from having a negative error where you're producing more power than you expected to a time where now all of a sudden you're producing less power than you expected. And so you're kind of hit with this double whammy where you've mispredicted in one direction and then all of a sudden you're completely wrong in a different way. And that can have serious repercussions on the grid because now you may have spooled up this reserve power, natural gas, and now all of a sudden, oh my gosh, we're producing all this extra wind, turn it all off now, so we can use the wind. And so it makes things very problematic when you're actually trying to manage a power grid. So this particular time period corresponds with here. You can see here the observations, that's when the ramp occurred in observations. And the power before, the model had the wind speeds higher before the event occurred. And so you were producing, you think, oh, this is great, I'm producing more power than I thought I would. I'm sorry, reverse that. See, I still mix up the terms, that's why I get confused, right? We're producing less power than we expected, but then all of a sudden the ramp happens an hour and a half earlier than forecasted. And so the way power is bid by PJM, that can be very problematic because you're actually producing, you initially have to put in a bid a day in advance and then you can refine it an hour before, and I'm not going to dive into all the technical specifics of that. But it's challenging. It creates challenges and instabilities sometimes in the grid. So overall, what did we find? We found, so as I said before, there are three primary types of error. First is that the timing error, where it may predict a ramp, in this case, several hours too early or too late. WRF was more likely to predict the ramps to be too early, at least in our model runs. For intensity error, the wind speed tended to be too high before the event. In the case of 9 of those extreme events and 5 of the analog events that took place. And the model completely missed 2 extreme events and 1 analog, where it didn't even see a ramp occurring. And then in terms of shape, WRF tended to predict ramps to be more gradual than they actually occurred in observations. And it often kept the wind speed too high after the ramp occurred. So a lot of times when you get a wind ramp, but the wind ramps up and then it kind of goes off a little bit. WRF often didn't predict that. It kept the wind speeds high. Alan?
I'm a little confused. Your large scale forcing for WRF, is it a forecast?
Yes.
So if the forecast was correct for the large scale, then you wouldn't have this area, right?
Perhaps. That's probably true, yeah.
Did you go back using a reanalysis and redo it, saying you pretend you have a perfect forecast?
We didn't no, we did not for this study, but I know that's something that we want to look at. And let me explain, I guess, I should have explained this a little bit earlier. The reason we did it the way we had done it, rather than using reanalysis, was we were trying to create an environment where an operator would actually be trying to predict what's going to happen when they're trying to sell power, right? So if you're trying to tell PJM how much power I'm going to give you tomorrow, we tried to set up a model situation that a developer might actually use to do that. And no, we didn't get a chance to actually go back and do that, but that's actually a really good idea too. And
the forecast was just the previous day?
Correct. Yeah, we were doing 1 day out, basically.
Joe, just to follow up on that, WRF is a regional model.
Mm-hmm. Yeah.
So were you providing information at the boundaries from reanalysis or from an operational forecast?
No, it was all from operational forecast models, yeah. And so in summary, it kind of helps demonstrate that some of the challenges in predicting a ramp when you're trying to predict for actual operations. But it's more than just the winds that are happening. And this is why we had someone like Yossi on our team who is an environmental economist. So here we have the green figure that I showed earlier that shows the electrical load demand over an average year, averaged together multiple years. And then this figure is the rate of change of that load. So you can see, everyone's turning things on, and so the rate of change is pretty high, increase. So red is more power demand, and blue is when, everybody starts turning things off. And so the timing of the event actually matters a lot. Because if you get a ramp right at one particular time, it's not going to have the same impact as one at a different point of time. So let's take this as an example. You're suddenly producing far less power than you had, far more power than you had anticipated. If that happened, it's like it sometimes works and sometimes doesn't. If that happened when power demand was not going up as rapidly, that could be a problem. More so than if it happened when everyone's turning things on anyway, you're going to need more power. Oh, we're getting more power, that's great. We can actually supply it to the grid. But if it happened, later in the day, that's not the case. Conversely, here, in this time period, where we're producing less power than anticipated, right, I got that, yes. Again, the timing matters. If that happened when power demand is already starting to level off, it might not matter as much because there's not as much demand. But if that happened, first thing in the morning when everybody's turning things on, that would have a bigger impact when you're suddenly producing less power than you expected.
Joe,
Yes.
question. This sort of assumes that power is not getting stored in batteries so much.
Correct. There was no storage in this.
Yeah. So you want the usage to ideally would coincide with the peak amount of peak usage would be peak winds or whatever.
That would be ideal, yeah.
Now, realistically, is that how these things work, or do they all have big battery banks?
For the moment, this is how things work. Granted, we don't have a lot of renewable energy yet. I mean, we're still in the the low teens in terms of total
So if
renewable.
there's a lot more battery storage for energy, then this would change a lot.
Correct, and there's been a lot of other studies, including some that I've been on, that actually look at that problem a little bit more, as to how much storage do you realistically need in order to minimize these kinds of problems.
And just real quick, how often are they rebuying power? Does that mean every day they buy power for the next day? Or? So
I'm going to try to do this in like a 2-minute snapshot. I have a whole chapter in my dissertation about it if you want to look at it. But so basically, as the way it was set up when I was doing my dissertation, so our grid operator is called PJM. And basically what PJM does is they buy the power from the people producing it, the power plants, and then they sell it to the power utilities that are actually selling you your power. Which is actually kind of interesting because, say, PSE&G, they both own plants and sell power. But in between, they sell their power to PJM and then buy it from PJM again. It's a weird relationship, but it works. And so what PJM does is it manages the grid and it makes sure that supply and demand are always equal. And that we're always providing enough power that we don't have brownouts, but we don't have so much surplus power that we're just spilling it and getting rid of it. So the way it works is the day before. So say you want to provide power tomorrow. Today, by I believe the timing was noonish, by around noon, you would have to say to PJM, if you were a nuclear power plant operator, you'd say to PJM, I'm going to sell you 600 megawatts of power 600 megawatt power production sustained tomorrow, because a nuclear plant, you don't really change the production that much. If you're a wind operator, you have to say, okay, based on the weather forecast for tomorrow, I can provide this much power at 8 o'clock, this much power at 9 o'clock, throughout the day, right? And so you have to do that the day before to give PJM an opportunity to figure out where it's going to get its power from for the next day, roughly. Then on the actual day of the power, the day that you're producing the power, that gets updated. There's an hourly window where you can refine what you promised to provide. You can't change it that much, but you can refine it. And then they also do 5-minute intervals of very rapid changes because they're very good at predicting load, but it's not perfect. And so that's when they have things like, so the grid is made up of a variety of different power sources. As we all know, things like nuclear or coal are typically considered baseload power generation because it's very hard to change the power output of a nuclear reactor, for example. And so you always assume, oh, it's going to produce 600 megawatts all the time. That, of course, creates a huge problem if all of a sudden they have to shut down the reactor for some reason. And so because of that, there are other sources of power that the grid relies on to fill in sudden gaps, which we call power reserves. There's a couple other terms for it, which are typically rapid response natural gas generators that can suddenly increase in power output in a matter of minutes. And so if you are suddenly providing less power than you expected, you have to get this reserve power. Reserve power is expensive. It's a lot more expensive than the baseload power that you were initially providing. And so that's where so like the grid, even though yes, you can bid your power at 5-minute intervals, in practice, they don't like doing it because it ends up being a lot more expensive, which comes down to us as the ratepayer, that our electricity becomes more expensive. Does that hopefully that clarifies that a little bit? Okay. So what does this mean for the grid, right? As I've said, ramps could have significant grid impacts. And so we determined there were 3 types of ramp errors. So this is a combination of the forecast error. Wow, I'm taking way longer than I thought. So we combine that with there's this large change in the error in the forecast. So the wind is completely wrong. That's one type of error. Another error here is where the wind forecast might not be that wrong, but you have a tremendous change in the expected load. And then this third type of error here is, again, you might have a modest change in the forecasting error, but you have a very high load demand day where you really don't have a lot of surplus power to go around. And so we have 2 different variants of those errors. The positive sign is the power surplus, and the negative sign is a deficit. And the negative events are more challenging, again, because you have to find that power somewhere else. So you have to ramp up natural gas, you have to buy expensive power. Whereas if you have too much power, you can either put it in storage if you have that, or you just dissipate it, you don't use it. Basically send it to ground. And so the 2 most common types of error are resulting from these large changes in net load. And ultimately, I'll summarize it real quickly here. Improving model performance specifically during the summer morning or the winter evening seems to be the times that these errors are most likely to occur. And so if we're trying to improve forecasting only in a very specific time window, that's kind of the sweet spot. And I'm gonna go through the third part relatively quickly, but I think that's okay. So now I'm gonna try to connect some of these dots. So we've got the ramp prediction, we've got these idealized setups that I talked about initially. Let's put them together and do some mesoscale resource assessments. And so now we're gonna take these 2 hypothetical wind farm shapes, and we're actually gonna put them off Delaware in the model, and we're gonna see how the power and the wind farm itself responds to actual, everyday weather, right? And so in order to capture this, you have to capture a lot of atmospheric phenomena. You have to make sure, because obviously, I was doing my dissertation at the time. I don't have time to sit there and run WRF for 3 continuous years, right? So I have to pick case studies that allow me to see overall, how different weather phenomena are impacting the wind farm without having to model the entire time period. And so you have to account for things like atmospheric stability, formation of things like low-level jets, which often occur when it's very stable at night. And those low-level jets often happen right at the height of the wind turbine rotors. So if you're measuring surface winds, you're not going to see those. And so we need to make sure to include things like different stability conditions. I have to make sure to include diurnal cycles, accounting for all sorts of type of variability. And so the way I did this is I used synoptic typing. And the technique I used was developed by Dan Leathers and his group down at the University of Delaware, which uses a very briefly, I'll summarize it as a principal component analysis where they use surface observations and NCAR reanalysis maps, basically area maps, to determine what the overarching synoptic weather conditions are. So a synoptic weather condition might be there's a cold front passing through the area, or there's a low pressure system off of New England, or something like that. And it's been used in a variety of studies, both at the University of Delaware and beyond, looking at things like hydroclimatology, lake effect snowfall, wind ramp events. We used that in that study. Some of my postdoc work looking at ozone pollution. And now here at Rutgers, we're actually using it for some coastal storm work. And so it breaks it down into 13 different winter types and 10 summer types. I'm not going to go into too many details there. But you can see that there's variability in the synoptic types. And so what I did was I selected random days that corresponded to the distribution of synoptic types. So I was trying to weight each synoptic type, weight my case study selection based on the frequency of synoptic types that you might expect. And I only did winter and summer because those are the two extreme seasons for wind. So this is the model setup. I had 4 domains. Again, I'm going to try to skip a lot of the technical detail. And then the layers in the model. So this is the full model height here, and then this red region is blown up here, so you can see the number of layers, the number of levels below 1,000 meters. And these 2 black lines here highlight what the rotor height, the rotor diameter would be of a wind turbine. So you can see there are multiple levels within that wind turbine rotor layer. And overall, the custom shape performs better than the rectangle. And so the black line that you can't really see too well, is the perfect 1-to-1 ratio. If the rectangular farm and the custom shape was producing the same amount of power, it would fall on the black line. And then all the blue dots are all the different model comparisons. And so overall, there are more blue dots on the custom shape side than the rectangle side. So as a couple examples, this is one summer day. I blew it up here so you can see the winds are coming out of this direction because you have a greater capacity factor of those wind turbines of about 60%. And here at the back, you've got a capacity factor of about 30 to 35%. And the custom shape, again, does slightly better, slightly higher overall capacity factor and average energy production by each turbine. Okay. Going back to the wake effects that I talked about earlier. So that picture I showed kind of highlighted wake effects within a farm. One of the strengths of WRF is it's a mesoscale model. So we can look more beyond just what's going on in the wind farm. In fact, within the wind farm, there are probably better tools to do that, like LES, like wind farm models themselves. So what I'm showing here is the wind speed reduction between the control case that had no wind farm and the case that had the wind farms. This here is near surface winds at 10 meters. And then this is up at hub height of 90 meters. And so you can see these wakes propagate pretty far, tens of kilometers, depending on the atmospheric conditions. So this is a particularly stable case where the wakes tend to last longer. When the atmosphere is less stable, the ambient mixing tends to make the wakes dissipate more rapidly. And then, you know, just for comparison's sake, this is the rectangle versus the custom shape. And the reason this is important, so this is the Delaware wind farm, the Delaware wind energy area. This here is very crudely drawn. The New Jersey wind energy areas, and then this here is the Maryland wind energy areas. Those wakes are propagating right into the New Jersey wind area. So when the winds are blowing out of this direction under stable conditions, the wind farms built here are going to be producing less power because there's a wind farm there. And so this is something that has to be taken into consideration in regional development. When you're building these wind farms, maybe we weren't so smart by putting them all in a line along one of the most predominant wind directions. But, you know, I guess it's kind of too late for that now. However, BOEM is learning from their mistakes. And if you remember the map I showed way earlier at the beginning, showing all those wind areas, those 4 different wind leases up in Massachusetts that are all right next to each other. And here in New Jersey, the 2 different wind leases that are right next to each other, they're not doing that in the future leases. They deliberately want to have buffer zones between the lease areas to kind of reduce this effect, because this is a business thing, right? If you're Ørsted in the southern area here and the winds are coming out of the south more often, you're going to be blocking the winds that US Wind gets in their northern lease area. And so you have a business advantage, right? And so they're trying to correct that moving forward. But it's important, and it's something the developers are going to be spending a lot of time working on. This is an example of a low productive summer day. But again, the custom shape still performs better than the rectangle. And so when you add this all up, during the winter, I saw about a 1.5% improvement using the custom shape. During the summer months, which again, that's where we have our peak power demand, I saw an increase of 2.5%. So, and a total of basically an additional 13.4 gigawatt hours, which is enough for an additional 1,200 homes, basically. But energy production isn't the only factor. in deciding how to lay out a wind farm, right? There's the actual lease area, cabling costs, platform costs, geological considerations. I didn't put on here fishing. Fishing's a very big one. And so you need to evaluate all of this in a holistic way in order to do it. So really quick, I'll talk a little bit about what's next, what we're doing here at Rutgers. So we run RU-WRF, the Rutgers real-time WRF model that we've been running since 2011 with BPU funding in order to do wind resource assessments. So we have a 9-kilometer outer grid, a 3-kilometer here in the purple, and then a 1-kilometer grid here centered over New Jersey. I won't get into too many technical details of how the model is set up because I could always give another talk on that. But overall, I give an example here. This is a 3-year mean of winds coming out of the model at 120 meters. You can see the wind speed varies from 8.5 to 10 meters per second. These other wind energy areas that I haven't talked about, these are called the New York Bight Call area. BOEM is investigating those areas as potential areas for new leases. And they don't plan to develop all of that. They're saying maybe about 20% of that area. But this is the area that currently is being very contentious, especially from the fishing communities. So RU-WRF, we can calculate all this stuff with mean data, but we also have all the data hourly. So you can actually go in and see what's happening on an hourly basis. And if I turn that wind speed into capacity factor using the 8-megawatt wind turbine, you get a capacity factor ranging from about 48% to 55%, which is pretty good. But what matters with wind energy, at least when you're doing a resource assessment, is not necessarily the day-to-day, hour-to-hour variability. It's how well do you capture the wind distribution, right? So here's an example of the 3-year, this is what we call a Weibull distribution of wind speeds. And then this black line here is a wind turbine power curve. And so basically it tells you how much power you're going to get out of the wind turbine at that given wind speed. So this particular turbine has a 12.5 meter per second rated speed, meaning once the winds reach 12.5 meters per second, it's producing full power, and any increase in wind speed, you're not going to get any additional power. And so once you don't really care what's happening up here. Once you get winds that are that fast, the wind turbines are producing all the time anyway, so you don't have to worry about it. It's all these other winds that matter. And so what this shows here, this blue curve, is showing the total energy produced in each wind speed interval by an 8-megawatt wind turbine over that 3-year time period. And why this is important is, so here's rated speed, 12.5, the dotted line. Roughly 60% of the energy extracted by that turbine was produced below that rated speed, which means if you're off in your forecast between 8 and 10 meters per second, you're at like, you're several thousand megawatt difference in power generation. And so capturing this low end is incredibly important in wind energy resource assessment. What are we working on next? So this is a figure that my student Brian put together. One of the other things we're doing is we're looking at how well, we have this real-time weather model. Let's see how it actually did at predicting ramp events. So he used that algorithm to pick out ramp events in the observations in red and then from WRF in blue. And this is looking at a couple different intervals of how long a ramp occurred. And if you remember earlier, I said that WRF tends to predict the ramps to occur more gradually than they actually occur in observations. You can kind of see that here. When we're only looking at that 1 hour time interval, the difference between what we see in the buoy and what we see at WRF is much larger than when you get at the higher ends. And so this is work we're just starting. Brian's doing his G.H. Cook thesis with me. So we're really excited to see this build into some new work. So what does this all sum up to? We need to figure out, at least for ramp events, what kind of weather conditions does the model do well? When does it predict it well? When does it not predict it well? And can we try to quantify that and figure out what we need to improve? What other factors might be coming into play? What about sea surface temperature? How much of an impact does that have on predicting the wind resource? Ocean heat content, the surface waves, things like that. And then of course the big one, I always like to joke, the land is not the ocean, right? And unfortunately, most of our observations of the atmosphere occur over land. And the ones we do have over the ocean are very scattered, and most of them are at the surface. Getting wind observations at height over the ocean there's very few places where you can get that data. And so we desperately need better observations of the atmosphere over the ocean. The wind developers are helping with this. They're putting in the floating LiDAR buoys, they're putting in towers. They're treating that as company proprietary data. And so us getting access to that is very problematic. In Europe, the European governments have put in money to build met towers, to build LiDARs off the coast that everybody can use the data. Our government hasn't done that yet. And so that's kind of, if I'm gonna have my political piece, if we had to push for something, that would be what I would push for, right? So here's my summary slide. I guess what I want to say here, the last point here, so why I was using the mesoscale atmospheric model here, it's a good tool, but there's lots of other tools. There's lots of ways we can couple it, either actually environmental coupling, so coupling it to the ocean, or coupling it with all these other tools that we have here at Rutgers to study problems as they relate to one another. So here's our little wind energy diagram for some of the experience that we have at REI, and how, today I only talked about this blue box. And I kind of dabbled a little maybe in a couple of these others. But I really want to learn more about what everybody else is working on. I've heard a lot over the recent few months of what folks are doing and how we can work together to really, offshore wind energy is an interdisciplinary problem. It's going to take interdisciplinary solutions. And we at Rutgers are uniquely situated to do that work. And so I'll leave it there. Tony.
Joe, do the winds ever get too strong for the turbines to operate?
Yes. So wind turbines have, we call it a cutout speed. And at that speed, the wind turbine shuts itself off, basically. So it feathers the blades so that it doesn't catch the wind. And for most commercial wind turbines, it's somewhere between 25 and 30 meters per second.
So that's something that's not going to happen too often.
Correct.
But that would create another kind of problematic ramping event, right? Where the power
Yes.
suddenly goes to zero.
Yep, that is another huge problem, especially because, they say, so it's a two-sided problem, right? They say, okay, the wind turbine shuts off at 25 meters per second. In practice, it might shut off at 24.5. It might shut off at 26.1. And then add to that the error in the wind forecast. And it is actually a huge problem that I did not delve into here at all. But that is a big thing. But what I will say is a lot of times when the wind speeds are getting that high anyway, it's because of things like tropical storms, hurricanes, nor'easters, events where the developer or the operator of the wind farm might be shutting down the wind farm as a precautionary measure anyway. So it kind of depends. But yeah, that is a huge question. Josh.
Joe, could you just comment on what gusts do to this analysis? When they're, the difference between a gusty day versus a steady wind day and how that's incorporated, do the turbines operate differently, or does the power purchasing change if it's a gusty day?
That's a good question, and I haven't looked at that specifically, but what I can say, so as you can imagine, these turbines are very large, right? So these rotors now, they're talking, the current rotor diameters are somewhere between 160 and 180 meter rotor diameters. There's a lot of mass behind those rotor blades, and so they've got a good amount of momentum. Once they get going, the gustiness in the wind doesn't impact it as much as you might think. However, so basically the way they work, so gustiness is not just wind speed, right, but direction, might shift a little bit. Each of the turbines have an anemometer, or at least usually 2 or 3 anemometers at the top. And so what it does is it basically averages what the winds are doing and points the turbine ideally for what, I think they usually use like a 10-minute average. And so it is a factor. I haven't looked to see how much of a factor it is. I'm sure folks are working on that though. I know a big question that we have, a big problem is, we've got these huge rotors. The winds change with height, right? And so I was part of a study down at UMBC when I was doing some work down there, that when they were doing LiDAR work they were using LiDARs on boats off of Maryland. The wind profile, very rarely was it actually like a log shape or a power law shape like we would normally expect. I think it was only about like 15% of the time. And so all the assumptions we're making are probably garbage. Right? And so that's a huge question that we don't have. And that makes a big difference. When you are calculating wind output, a lot of times we just use the wind at hub height, right? But the winds could be a lot higher up here than they are down here. That's also a huge engineering problem, right? Because you're putting an enormous amount of stress on these blades when the winds are changing that rapidly. And so that's another huge question. Alan?
Don't they have LiDARs in the hubs pointing in the direction of the wind so they can see the wind coming in?
Yes, I don't know how common they are, but they certainly exist. Because I know I've seen some data from some of those. It's great because you can see the wake effects. You can see all sorts of beautiful things with those LiDARs. Yeah. But I don't know how common they are. Like if they're installed, like if every wind farm has one or two, I'm not sure how common they are though.
So the marine boundary layer tends to be stable a lot.
Yep.
Second, oftentimes you end up with low-level cloudiness. And my question involves actually the turbulence that you generate relative to that low-level cloudiness. So in previous experiments in the marine boundary layer, we've taken ships and we've run them through areas that had low-level clouds in the quietest conditions like this. And we've seen pretty profound changes without doing anything else to the cloud structure downstream. So I'm wondering, do you see wake clearing effects?
That's an interesting question. I don't have an answer to that. But I had never thought about that, but that's, I think that's something worth looking into, right? So yeah, so like the wake's actually dissipating some of the clouds that form.
Or enhancing.
Yeah.
It could be both.
Well, like you saw that photo, right? You're getting the clouds that were introduced because of the wakes. Oh, that's fascinating. That's a really good question.
And also, I just want to point out, if you, while not specifically this area, if you want over-ocean wind profiles.
Say it again, sorry.
If you want some over-ocean wind profiles in a lot of data.
Excellent. And of course, we've got, oh yeah, and we've got the wind tracer now that we put up that we finally got running down in Tuckerton. So we're able to start seeing some wind profiles off of the coast now. We're still working on getting all the other stuff set up for that, so I haven't really gotten to play with it yet. But
I just have one more quick.
Sure.
So one of the problems I saw in your sort of shadow effect, you have a line, so you see turbulent wake off the first one, and it's generating right down the line and all the rest of it. It makes me wonder why you wouldn't try to control the distribution of the TKE that you're extracting as you go down the line. In other words, put resistance on the first one and less resistance as you go back, so that you don't create an enormous turbulent wave from the beginning, but you level out your extraction of TKE over the run.
So almost, I guess the suggestion is that basically scale back on what the wind turbine is extracting in order to reduce. Right.
Flow, because it's
Right.
basically blow the turbulence crazy.
Yep.
Rather break the first one slightly and then let the rest of them free flow at a more linear rate. That way you extract TKE more smoothly.
Right, and I actually believe some of the wind farm operators are doing that now. They're kind of hampering the production of those frontline turbines in order to enhance production at other turbines. And of course, it's always that balance of, all right, so you give up a little bit of power at the front, do you gain more? And I guess it works because they are starting to do it. So that's great. Dunbar.
So these mapping events happen when the forecasting isn't good enough for what you're having. And so obviously you harvested the air for many quarters past. Do you understand why those events happen meteorologically?
So that's one of the things, we kind of dove into that a bit in the paper in terms of, so we were identifying it using the synoptic typing method of, which synoptic types are more common, ramp events more common. We kind of dove into that a little. That's actually our next step. With the work that Brian is doing, I'm still working with Dana. Dana was actually up here yesterday for a research meeting with us. We're taking that to the next level of actually diagnosing, okay, under these meteorological conditions, the model does a good job. Under these meteorological conditions, it does a terrible job. Why are those conditions different? It's good at cold fronts maybe, but it's terrible if it was caused by a sea breeze. I'm just throwing those out. I have no idea if those are true. And that's the next step. That's what we want to do next.
So just following up on Dunbar's question and something that Mark alluded to, and maybe you've done this already, but have you looked at the role that inaccurate forecasts of static stability may be playing on the forecasts of wind?
No, we have not looked at that yet.
Because these are areas where the static stability can change dramatically. And it will also depend on how accurately sea surface temperatures are being represented in the forecast model. Because often the variations in static stability are driven by sea surface temperature anomalies.
Right. Yeah, that's not something we've looked at yet, but in this next realm of the study, so with RU Wharf, we use our high resolution coldest pixel sea surface temperature product as that bottom surface. With the runs that I did when I was a grad student, obviously I wasn't using any special SST data, I was just using climatological data or whatever was available in GFS. So that's something we want to look at next, is what role does that play in improving the forecast on that.
Coldest pixel or warmest?
Oh, we're using a coldest pixel algorithm that we developed here at RU Cool. So what it does is, the problem we have off of New Jersey is we often have cold coastal upwelling that conventional warmest pixel methods treat as clouds. And so you end up losing all that cold water that we get off of New Jersey. It says, oh, that's a cloud. That's not actually sea surface temperature. And so we have an algorithm that, is Crowley still in the room? No, but I know Laura's here and she works on this too. But so what it does is it combines the visual satellite image and the temperature image to be able to exclude clouds, but still retain that cold water.
So it only works during the day.
Correct.
So I have to go. I know some of you have to go, but this has been a very productive conversation, and I welcome you guys to come talk to Joe.
Please, I'm here. I have a conference call at 2, but nothing until then. So.
Let's give him one round